Okay, this last tape here is going to be based on the energy of simple harmonic motion. So we have a mass that's oscillating, right, between negative and positive amplitude extreme positions at 1 and 3 there. So we're just going to look at the energy at each of these times. Now, if we're going to assume that there is no friction here in the system, all right, the total energy of the system the whole time is going to stay the same. No energy will be lost. So every time that the spring compresses, okay, energy is stored in elastic potential energy. This is different than the typical potential energy we've dealt with. The typical potential energy we've dealt with has been gravitational potential energy. We now have a new potential energy, which is elastic potential energy, okay, which is the energy stored in the spring. When you compress a spring, there's no movement, but there is energy stored because when you release it, there is movement then, okay? There's a conversion between potential to kinetic. So between all of these, assuming no friction and no heat loss, the total energy stays the same, okay? But at positions 1 and 3, okay, we look there and we should remember that the velocity at those times is equal to 0. So if the velocity is equal to 0, what is the kinetic energy equal to at those times? 0. All right, good. At the equilibrium position, position 2, we know that the spring is not stretched at all. If the spring is not stretched, no energy is stored in the spring. Therefore, the potential energy at the equilibrium position is also 0. So we can basically just fill in the blanks here that the potential energy when it's at the amplitude is at its maximum, okay? And that therefore the velocity is at a maximum at the equilibrium position, so the kinetic energy is at a max at that position as well. So let's take a look at these derivations. Quick little bit of calculus here, okay, sorry. But the change in potential energy in a spring is going to be equal to the negative work done on, the system, which is the negative work when we talk about energy in thermodynamics. We'll explain what that means, okay? So what this effectively says is that if we consider the integral of the force with respect to position, all right, from the equilibrium position to the maximum displacement, okay, or any displacement really, what we end up with here, okay, is the following. Remember, we're talking about the spring force, all right? Oops. And we're going to call this S here. Here we go. And when we do this, we evaluate this, it's going to be 1/2 k s squared from 0 to x. All right? So basically, it's 1/2 k x squared is what the change in potential energy is going to be equal to. All right? So if we assume that the initial, all right, we're just going to take the stored potential energy in the spring to be 1/2 k x squared. Okay? If you didn't understand how I did that, that's okay. This is just showing you how we get here. All right? All you need to know is that this is the formula for the potential energy stored in a spring. The kinetic energy is a bit easier, all right, to understand. The energy stored from the kinetic energies, we know is 1/2 mv squared, okay? And we're going to substitute a formula in here. The v is equal to plus or minus omega times the square root of x naught squared minus x squared. And there's something I want to remind you of really quickly here, okay? Omega is equal to the square root of k over m. We've already shown that. And if we solve for k, it's just equal to m times omega squared. Just a quick thing to point out here. So, all right, 1/2 m omega squared. The plus or minus disappears, it goes away, right, when we square this whole thing, times x naught squared minus x squared. All right. We can also write this as 1/2 k x naught squared minus x squared. So these are the two different formulas we can use, all right, for the kinetic energy. Either one's acceptable. And the total energy, right, is just equal to U plus K. And if we substitute this in here, we get 1/2 k x squared plus 1/2 k, and I'm going to distribute this, all right. And what we end up with is that the total energy is just equal to 1/2 k x naught squared. So we see that this total energy stays constant no matter what, as long as the amplitude stays constant. And sometimes this may also look like the following. And actually, let's rewrite this E total, just so you don't get confused. But the total energy can also be rewritten as that. You will also see that, okay? Know that the difference between the total energy and the potential energy is the displacement at any point, okay? It just gives a description of the state of that mass. The total energy, all right, is the entire system. If the amplitude stays the same, then that equation holds, all right? What do you see here? What's special? What do we see that the total energy is proportional to? Well, we see the total energy is proportional to the mass. Total energy is proportional to the frequency squared, really the angular frequency squared. And we also see the total energy is proportional to the amplitude squared. Okay. Just some things to note and be aware of. If we analyze this, the energy versus displacement, we get a couple of interesting curves here, okay? The two curves that we end up with here, remember the kinetic energy at displacement, the amplitude is equal to 0, but at displacement 0, the kinetic energy is the maximum. So the kinetic energy curve looks something like this, okay? And the potential energy curve is at a max at the amplitude, ends at 0 at the equilibrium position. So the potential energy curve looks something like this. There we go. Not drawn too well there with the kinetic energy one, is it? Let's see if we can do a little bit better. Okay, that's a little bit better. Oh boy. Okay. And the total energy is constant the entire time. So let me just quickly label these. This is the potential energy. This is the kinetic energy. All right. And your total energy curve, right, does not change. Okay, there we go. A quick note. I would like you to see the energy-time relationships here. All right. Oh yeah, let me just rewrite the energy displacement functions for you as well. I think it's important to have these for you to look at. So, potential energy kinetic energy. I want you to get used to seeing them, both formulations, one with m omega squared and the other with k. All right, there we go. That's it. Really quickly, you'll see the energy versus time. If we consider U, well, if we substitute x squared, all right, for our displacement function, what we end up with here is the following. Okay, and then we can do the same thing with the kinetic energy, so we just need 1/2 mv squared here, right? And when we do that, we end up with 1/2 mv naught squared times cos squared omega t. Okay, so if we look at energy versus time, right, and then this is going to be half the period, full period here. Right. We know the total energy is going to be the same. I don't know what just happened there. There we go. The total energy is the same. And the potential energy curve, right, since it's sine squared, that's going to have to start, let's see here, it should start at 0. I don't know why I don't have it drawn such here on my paper, but right, so the potential energy curve should end up looking like the following. right? I believe that's your sine squared, right? So this is EP, okay? And let's see here, let's get the kinetic energy curve on here as well. Okay. And that's the kinetic energy curve over time. So that's just to give you an idea of what the energy looks like over time. You have energy versus displacement there, and energy versus time here. I know you don't have it in your notes specifically, but I think you should have it as a little extra thing, maybe write on another piece of paper. Okay? Hopefully you've watched this far. So let's take a couple of examples. These are the same examples I asked about before. What happens when we double the amplitude? What is the effect on the masses, period? Well, we already answered this question, okay? If we double the amplitude, okay, the period is the same, but what happens to the total energy? Well, if the amplitude is doubled, the total energy is increased by 4 times, all right, because you're squaring that amplitude. Well, the second one asks, what if we double the mass? Well, I showed before that the period is the square root of 2, 1.4 times larger. Okay? The energy stays the same. Whoa, didn't you say, Chorman, that the total energy depends on mass and frequency? Well, yes, I did. Okay? But those effects will end up canceling each other out. All right? The reason that it cancels each other out, right, if we come back to what we had done before, where was it? Yes, 1/2 m omega squared times x naught squared. Okay, that m times omega squared, right? We've increased the period by the square root of 2 times. Well, if we double the mass, and remember, this is just the same as 2 pi all over t, and we increase this by the square root of 2, and sorry, this whole thing is squared. Okay? We are, the square root of 2 in the denominator being squared is going to cancel out the 2 there. So the overall factor by which it's increased by is just 1. Alright? So do the math there. You'll see it works out that because the period is in the denominator of omega, that the effect cancels each other out. If you're not convinced, consider this formulation for the total of energy. Do we change the stiffness when we change the mass? No. Do we change the amplitude? No. No effect. All right? That's it, guys. Happy note taking. See you Thursday.